let's start. Before we'll go into the topic of today's seminar, I would like to present the seminar series a bit and our lab. So this is a seminar series related to programming languages and tools lab at JetBrains Research. So on the display, you could see the current staff of the lab. So we have 4 researchers in the lab. And our topics of interest are programming language semantics, weak memory models and concurrency, certified programming and mechanized proofs, relational logical programming, metacomputations and partial evaluation, and formal languages and theory. So we do fundamental and applied research in these areas. If you are interested in collaboration, please contact us. You can find our contacts in Meetup page, or you can mail to me directly at anton@podkapaev.net. So in this series of seminars, we plan to have different talks related to these topics. And in the first couple of meetups, we'll present different research areas which are interested for us. So today it will be weak memory models, which are topic of my research. One general comment: if you have any questions during the talk, please feel free to interrupt me at any moment. So let's get to weak memory models if there is no questions. As you probably know, in the last years, most CPUs got multiple cores in them. So now they do parallel execution, and this is kind of an answer to the problem with frequency of individual cores not growing as fast as it used to be. As we can see from this graph, starting from around 2005, frequency stalled. It's there is no increase in CPU frequency as it used to be, but CPUs got more and more logical cores. So it means that concurrency, and especially shared memory concurrency, is required for your applications to be high performance. And to write concurrent programs, you need to be able to reason about their behavior. So you kind of need precise semantics of the concurrency in the modern CPUs and programming languages. So such semantics of concurrency are called memory models. And in this talk, we'll see which kind of memory models are there. So the first memory model, and like the most famous one, was proposed by Leslie Lamport in his paper in 1979. The paper was called "How to Make a Multiprocessor Computer That Correctly Executes Multiprocess Programs." So from the title, it's kind of look like there was already an answer to the problem, and this answer is called sequential consistency. And in this memory model, in this concurrent semantics, all individual behaviors of concurrent program could be explained as some interleaving execution of threads over the single memory. So graphically, it could be depicted as the system could be depicted as like having one global memory and like a number of CPUs, and each CPU executes a sequential program. And once the program does a write, it writes to the global memory. And once the program reads something from memory, it goes from this main memory. Now let's take a look at some example of concurrent program and see how sequential consistency defines its behavior. So suppose you have a shared memory cell called data, and one thread writes to the data, and the other thread reads from the data. And suppose the data type of data is bigger than word in computer, so it's actually the read is split into two accesses. So then if we want to prevent strange values to be read, in a sense anything except for initial value or this value, here we need to kind of guard the accesses. And there is a standard solution for that called locks. So you could lock the accesses to the data such that these locks would forbid simultaneous access to the location from both threads. Now, yeah, and suppose these locks are implemented as Peterson locks. So let's take a look at their implementation. They use, each thread has a flag, and also there is a shared location called turn. And what the Peterson's lock does, first a thread sets its corresponding flag, and then says that actually it's now a turn for other thread to execute its synchronized block. So the left thread assigns turn to 1, and the right thread assigns it to 0. And then each thread waits until it's turn of the thread, and it waits for the other thread to assign the flag. So does it really works? In theory, it does work. So there is no sequential execution of this, sequentially consistent execution of this program, which would lead to any problem. However, if we execute it on a laptop with x86 machine, there is something interesting there. So let's take a look. So I won't do the execution of this concurrent program now. However, you may believe me that what I'm showing you was reproduced on my x86 machine. So here we do a slightly different program, but more or less the same. So the idea is that instead of this data, which is bigger than the word on the machine, we have two arrays. Sorry. Array A and array B. And what we do in the left thread, which here is called thread 1, we assign value 1 to both cells of array B. Whereas in the right thread, we read from the B array and put the values to array A. And these accesses to A and B are guarded by the Peterson lock, the one we already saw. So in the main program, what we do, we assign both arrays to zeros, then start threads, then wait for the threads to join. And actually, we do this a number of times until we find either until there is something which is not both zeros in A or both ones in A. So if the Peterson's lock works, then we would expect to never this program to terminate. However, if we execute it, we may see that it terminates after 18,000 iterations. So something is wrong, and we'll need to understand what is going on there. And actually, the problem is kind of related to these accesses to flags, to flag 0 and flag 1. And the question is if it's possible for both read accesses, flag 1 and flag 0, to get 0, even if we remove the last lines, which used to unlock, which used to be a part of unlock in patterns unlock. Yeah, someone already wrote that an answer to the question, and actually, yeah, we'll get there. However, it will be something before I use the that words from the message. So let's simplify example, and instead of like having the whole Peterson's log, we'll just deduce the accesses to flag 0 and 1, and actually here I renamed them to X and Y. So let's once again look at the these accesses. So here we, in the left thread, we do write to flag 0, and in the right thread we do write to flag 1, and then we do reads. So let's simplify our example. Again, we initialize both location X and Y to 0, and then we start 2 threads, and each thread performs writing 1 to the corresponding location, and then we read from the opposite one. So here we could even use it as a part of synchronization. So we expect that we'll never get A and B being equal to 0 because there is no sequentially consistent execution which leads to this outcome. And this program, it's called Decker's log. And if we'll take a look at values which could be assigned to A and B after executing the program, it's obvious that we could get A being equal to 0 and B being equal to 1. To achieve that, we need to first execute the left thread, then the right one. In the same similar way, we could get A being equal to 1, B being equal to 0. To get that, we need to first execute the right thread and then the left thread. And we could also get the result A equals 1, B equals 1 if we first execute assigning instruction the left thread, assign instruction the right thread, and then do the reads. However, there is no sequentially consistent execution leading to A being equal to 0 and B being equal to 0 at the same time. So if we check this program being written in C++, we will see that still we get a result that the synchronization doesn't work. So why does it happen? So here, what I did, I compiled the program with G++ compiler. And also, I produced an assembly code for this program. So we'll take a look at it. Right. So in the thread 1, as in the previous slide, we do first writing to X1, then reading from Y. In thread 2, we do first writing to 1, then reading from X. So if we take a look at the corresponding assembly code, we could take a look at particularly these 3 assembly instructions. So here what we do, we first write 1 to Y, then do a read from X. So actually the reading is split to 2 instructions because we need to read through a register. And if we take a look at the program, here, everything is fine. It's exactly what was there. However, if we take a look, let me relate these two pieces of code. However, if we take a look at the corresponding code for the thread 1, it will be here. So here what we do, we first read from location Y and put the value to register EAX. Then we write 1 to X. Then we write the value to location location A. So actually, what we did, not we, but G++, it rearranged the instructions comparing to what we had in the program. And why it happened, actually G++ is allowed to do rearranging of accesses to the different locations, and compiler could deduce that X and Y are different locations, so there was no problem with rearranging it. So as we can see, compiler optimizations might violate our expectations for concurrent code. Okay, so what we could do, we could try to somehow forbid GCC from reordering instructions. So to do that, we could insert empty assembly instructions. So here we did this, and here we did this. And if we now take a look at the compiled code, we'll see that in both of the assembly pieces, the first instruction we do is the right instruction. So the arranging is not happening. However, if we execute the program once again, we'll see that we still finish execution with, in this case, after 800 iterations. So still it's not enough. And the problem here is exactly related to the comment which was in the chat. There is some buffering of writes happening in x86 architecture. So to briefly explain what is going on there, then x86 CPU performs a write to memory. It's allowed to buffer the write, to put it in some buffer, which is later flushed. So it means that, for example, let me draw something here. Suppose we have our main memory, which is in the beginning of the thread executions, is assigns both x and x and y to 0. Then suppose we have our CPU 1 and CPU 2. So once CPU 1 tries to perform this instruction, instead of writing directly to memory, it writes to some write buffer, which later might be flushed to memory. So we executed this instruction. Now we execute in a similar way instruction in the write thread, assigning 1 to y. So now we could execute the reading, getting a being equal to 0. Then we could execute read from x, assigning b to 0. And then later, the CPU 1 might flash its buffer. And the same could happen with the write thread. So now we need to somehow forbid x86 from buffering writes in this particular case, and there is a way to do so.
Anton?
Yep.
There is a comment in the chat that there is no flushing. The buffer is drained to the coherent cache as fast as possible. Can you please elaborate?
Sorry, I'll open. Okay. The buffer is drained to the concurrent cache as fast as possible. Okay, so the problem is that we could argue about that in the sense that we could start chatting about some particular execution of implementation of x86 machine, x86 CPU, and it actually, like, in the next generation of CPUs, Intel or AMD could do something different. So here I'm not actually like speaking about what happens internally in the CPU, but I'm more. But I actually am speaking about some mathematical abstraction over it, which is officially recognized by the CPU, the companies producing the x86 platform. So yeah, and actually later on in this talk, I'll be also referring to some mathematical abstractions over other CPU architectures. So even though there might be some other explanation for a specific CPU, it should have the same semantics in the sense that it will produce the same behaviors as here. So yeah, so you could say that the buffer is directly drained to coherence cache. Still, this behavior is observable. Are there any further comments on this question? So there is a question. So basically, x86 is compliant to that architecture, but it isn't actually built that way. In a sense, so essentially, the CPUs they have to be built according to some specification, and in specification states something like that. Yeah. So actually, it's not completely true, but we could think for now about that. It is like that. Yeah, okay. If there are no further comments or questions on this regard, let's continue. So what we could do to solve the problem, and yeah, I guess everyone recognizes that it's some kind of problem, because we want, in some cases, we would like to force this program never terminating with A being equal to 0 and B equal to 0. And there is a special instruction in x86. It's called mfence, which stands for, obviously, for memory fence. And what it will do in terms of the abstraction I just showed, once you execute the instruction, this write buffer will be flushed to memory, or you could think about it in the opposite direction. You couldn't be able to execute the instruction until the buffer is flushed. So that would prevent from getting the outcome A being equal to 0, B being equal to 0. And in the C++ code, we could do it with this inline assembly. Essentially, we insert this mfence. And now if we'll try to execute the program, you won't be able to observe any behavior with outcome A being equal to 0, B being equal to 0, unless there is some problem with your particular CPU. But according to specification, you shouldn't be able to observe it. Okay. So what we learned from here is that sequential consistency does not explain the current CPUs, and due to not only current CPUs, but actually the current pipeline, for programs. So a compiler could break it, and CPU architecture could break it. So we need something else. And the answer to that is so-called weak memory models. So any non-sequentially consistent behavior like the one we just observed is called weak, and memory models or semantics of concurrent system which allows more behaviors than sequential consistency is called weak memory model. And like real systems with concurrency, like all major CPU architectures and programming languages with concurrency, they all have weak memory models. And later we'll see why in this talk. Here some quiz for you. You could think about it during the talk. Here we have a slightly different program. Instead of doing writes as the first instruction, we do it as the second instruction, and we do reads as the first instruction. So as always in this talk, all shared locations are initialized by 0. So the question is, is it possible to get A being equal to B being equal to 1 in the end of execution of this program in x86? So if someone already has an answer, then please turn on mic and answer. If not, could wait like a minute or go further. By the way, there is some comment saying that TSO is a strong memory model. Actually, this is rather discussion on like terminology. So I would prefer not to go there because some people say that TSO is a strong memory model, but I prefer to say that strong memory model is sequential consistency. But yeah, it's just terminology. There is a statement about acquire and release semantics. Yeah, it's there. However, I'm just calling memory models which weaker than sequential consistency as weak ones. Okay. Any other question or answer to this problem already? Okay. So actually, the answer to the question is that you cannot get the outcome, this outcome A equals B equals 1 in x86. However, you could get it in memory models of ARM and Power architectures. And actually, it's called like load buffering. And as it's obvious from the name, it requires something which is dual to store buffering, which we saw in the previous example. So here we kind of expect loads to be buffered to be executed after the writes. There is some graphical representation for the architectures. Okay, so now to summarize, let's take a look at the big picture. So we have different memory models for CPU architectures. All of them are slightly different. Some of them allow one weak behavior, some disallow weak behaviors of particular shape. Like we saw, for example, store buffering. This is some weak behavior which observed on all the architectures, and actually it's kind of hard to disallow in the architecture in a sense that it's expensive to disallow it. But load buffering is not observable on x86, and it is on Power and ARM architecture. Then you have compilers, which also may introduce additional weak behaviors, as we just saw. GCC may reorder some instructions, and actually LVM kind of does the same. I mean, the GCC and the LLVM they do slightly different optimizations, which may lead to different weak behaviors. However, yeah, they all have some kind of way to introduce them. Then on the top, you have programming languages. They also have memory models, which even weaker than what is provided by GCC and CPU architectures. And the reason for that, because you want to essentially allow more compiler optimizations and be able to introduce new ones in the next years without changing the specification of memory model of a language. And then in the end, we have software developers who need to understand the models if they want to write log-free code. Okay, so now let's get to a section where we discuss requirements to memory models with a focus on programming language memory models. So as we already saw, as I already mentioned, hardware and software has different memory models because one of the reasons is that they have different requirements. Thus, hardware memory model requires to describe real CPUs, so any behavior which observable on proper CPU, let's say x86 CPU, it should be allowed by the specification of the architecture. So this gives us somehow a lower bound for behaviors which could be which should be allowed by the memory model of the architecture. Also, the memory model of architecture should allow some extra behaviors if it wants to save some room for future optimizations. So let's say if the next generation of CPUs Intel decides to introduce some additional optimization, it should be compliant with the specification. So specification should be weak enough. And as the first point, it also pushes the memory model to have more behaviors. And the third requirement, which actually gives us upper bound on allowed behaviors by memory model, is that we need some reasonable guarantees about behavior of the concurrent programs. Because if we would try to comply only with the first two, then it would mean that we could allow any behavior for any concurrent program, but obviously that won't be nice guarantees for programming languages which will be compiled to the architecture. So what about programming language memory models? As we already saw, compilers do some optimizations. So if we want the optimizations to be correct for the language, we need to allow them. And it pushes the memory model to be weaker to allow more behaviors. The second requirement is that we would like to provide efficient compilation to hardware, and that essentially means that the memory model should be weak. A memory model of programming language should be weaker than memory models of target architectures. And the third requirement, which is currently vaguely specified, but I'll specify it a bit more in more detail a bit later in my talk. Ideally, a programming language memory model should have an easy non-expert mode, in the sense that it should be easy for non-experts to write concurrent code using the memory model. Okay, so we'll focus on requirements to programming language memory models, and let's take a look at what it means for a memory model to support compile optimizations. Suppose you have the following program, which we already saw. This is the first program, the store buffering. As we saw, GCC may reorder instructions in the thread, leading to this optimized program. And as we already discussed, this program may end up with outcome A being equal to 0, B being equal to 0. Let's just repeat how to get it. For that, you need to execute this read. You'll get A being equal to 0. Then you execute the right thread and assign 0 to B. And then you finish execution writing 1 to X. And this outcome is disallowed for the original program. So essentially, if we want to make this optimization correct in our programming language memory model, we need to preserve the inclusion. So here we use the square brackets to define the set of possible outcomes for a program. So essentially, this is our semantic function. And it says if we want to be able to do the such transformation, it means that all behaviors allowed for this program should be also allowed for this program in our formalization. So the other requirement I mentioned is that we would like to have efficient compilation schemes from our programming language to target hardware. So for example, if we define our new version of C++, you would like to compile to x86, and this version, we would like to support sequential consistency memory model and nothing else, then we could do that. In general, it would require to put a memory fence instruction in between each memory access in our program. And unfortunately, there is a problem with such approach because the compiled program with these memory fences, it will be slow because the execution of these instructions takes a lot of time, basically due to requirement to synchronize the write buffers with memory. So in practice, it's slow. And this compilation scheme we want to call efficient. And the other requirement which I mentioned is easy non-expert mode. So essentially, at the top level, we would like have a property of a language saying that if you write only nice programs, then you get only nice behaviors. And let's make it a bit more precise. We would like something saying that if you have no data races in your program, then you get only EC behaviors. So what is the data race? Actually, it's defined slightly differently for different languages and different models, but the general idea is that data race is a situation where you have two concurrent accesses to the same location, and one of the accesses is write. The other one could be either write or read, such that there is no clean order between them. So like in terms of Java memory model, it's or C++, it's like different versions of so-called happens before relation. In sequential consistency, actually, the definition is much simpler. So since sequential consistency, as we discussed, could be explained by some interleaving execution of threads, a data race is essentially a situation where you could proceed in different threads with access to the same location. So as I said, there is some easy definition of data races in sequential consistency, and there are some more complicated, more complicated definition in C++ and Java, which uses some internal notion of happens before. And this is exactly kind of problem. So ideally, we would like to provide for software developers an abstraction which says that if you have no data races in sequentially consistent executions of your program, then you get only sequentially consistent behaviors. Basically meaning that it's for many programs, it's just enough to know sequential consistent memory model and nothing else. And this criteria is called data race freedom guarantee. So like, for example, let's take a look at the following program. So here, it's kind of like the load buffering example, which we discussed earlier. So we, again, have a reading happening before writing in both threads. However, now we also have a control dependency in both threads. So let's try to execute this program in sequential consistency. In sequential consistency, you start with either performing this read or that one. In both cases, you'll get the value 0 because this is what written to memory initially. And after that, you won't be able to continue with executing the going to the then branch of ifs in both cases. So the only outcome of this program in sequential consistency is A being equal to 0, B being equal to 0. So here in this program, there is no data race in terms of sequential consistency. Since there is no situation there, you could execute either this instruction or let's say this one, because you never get to the configuration where you could execute simultaneously them. However, if you take a look at the specification of C++ memory model, then you will realize that you could get A equals B equals 1 in this example. So essentially, in basic terms, it means that C++ memory model does not comply with the data race freedom guarantee. And this is like a weak spot of C++ memory model, which we will discuss in more detail in this talk. And it's called out of thin air problem, or UTA. Like similarly, if we slightly change the program to here, oh, sorry, let's keep for now the program as it is. Okay, so any questions up to this point? Okay, then let's discuss the existing memory models of programming languages. And so we have our three main criteria. I already mentioned three memory models: sequential consistency, Java memory model, and C and C++ memory model. And in terms of compiler optimizations, which is our first column, as we saw, sequential consistency does not allow all compiler optimizations which are performed by real compilers, or even ones which we kind of expect to be good optimizations. But still, sequential consistency allows many compiler optimizations, as you may see in this table. So, like for example, if your compiler optimization does not change order of memory accesses, so or it is so-called trace preserving transformation, then it's fine in sequential consistency. Although reordering of normal memory accesses, as we saw, is unsound in sequential consistency. However, like for example, redundant read after read elimination is fine, which is not true, which is not always supported by a memory model. So redundant read after read elimination is the situation where you read twice from the same location. So essentially, you would like to rewrite that code to be like that, assuming that A and B are local registers and not shared between threads. Okay, so however, we might try to force a compiler to preserve sequential consistency, and there is a research paper on that topic. So in 2011, there was a paper showing that you could modify optimizations done in LLVM to preserve sequential consistency. And if you do that, you may end up with 5.5 slowdown on big benchmarks. If you just turn off LLVM optimizations, which break sequential consistency, then you'll get much more slowdown. So this 5.5% looks not that big pay for preserving sequential consistency, although it might not be acceptable in many cases. And also, as we discussed, in this way, we just preserve, we just eliminate compiler from the equation. The CPU architecture still could do some optimized executions of the programs and lead to weak behaviors. So this is not the full price we'll have to pay. The other drawback of such approach is that we need to modify existing compilers, and that's a lot of work. And so this is actually not the way the this field of weak memory models try to go. So here we actually try to modify the our mathematical models to get the properties we expect, not to modify compilers. I mean, maybe modify compilers, but in like very tiny bits, not rewriting the like many optimizations in them. Okay, so what's about Java memory model? And surprisingly, Java memory model has arguably the situation which is worse than in sequential consistency in terms of supported optimizations. And so here now we have a column for Java memory model in the table. And for example, for Java memory model, redundant read after read elimination is not supported, unlike sequential consistency. Okay, what about C++? C++ arguably has a very good situation in terms of supporting compiler optimizations. So yeah, in this regard, C++ is better choice. However, what's about compilation to hardware? So as we already saw, if you compile sequential consistency to x86, you'll have to insert memory fences from time to time, and it will produce less efficient target code. But yeah, I guess it's kind of interesting how much we'll have to pay. And there was a work showing exactly that. And it was some experiment on Java virtual machine, which has like a similar guarantee like data race freedom, which essentially says that if all locations, shared locations in your program are marked with a special tag volatile, so it would lead the situation that you don't have data races, and that should give you sequentially consistent semantics. So essentially, if you mark all accesses in your program as volatile, you will restore sequential consistency. So in this particular work, the authors did something a bit more clever than just putting volatile to any access, but still it doesn't give very nice results in terms of performance, as we will see in a minute. So in that line of work, the researchers did the experiments on x86 platform and on 2 ARM servers with many threads, and they tested the solution on 2 sets of benchmarks. So the first one is the kappa benchmark, which includes like many big programs written in Java with, for example, Jython, the Java Python compiler. And the second set of benchmark is Apache Spark performance tests. So with the approach of inserting volatile accesses to shared memory locations, the slowdown on the x86 platform was about 28% for the kappa benchmark and 79% on average for Apache Spark tests, with maximum slowdown 81 and 164% correspondingly. And yeah, so it's already quite a big slowdown. It might not be crucial for some applications, but still kind of big. But for ARM, situation is worse. So on average, for both servers, it was more than 50% slowdown, with maximum slowdown for Apache Spark being Apache Spark test being marked as infinity. So here, infinity basically means that it was more than 1000% slowdown. So it was very big. So as we can see, ARM for ARM, this is not a solution at all, and this is due to ARM being much weaker than x86 platform, allowing much more weak behaviors than observable on x86. Okay, so this explains this angry face for sequential consistency and efficiency of compilation to hardware. For Java, the situation is rather good. For C++, it's very good. Why I'm saying that for Java, the situation is not ideal is actually because there is a known bug of compilation of the main JVM hotspot to power servers, in a sense that they compile volatile accesses without enough of memory fences, and that leads to behaviors which should not be observed. However, when we discussed that with the member of Java standardization committee, they said that they know about this problem, but they don't want to solve it because a lot of code will be slowed down quite a bit due to fix. So yeah, there are some problems with Java. And so what about DRF guarantees, which I already mentioned? So in C++, everything is fine. So I'll just remind you that data race guarantee says that if you have no sequentially consistent data races in your program, then you have a C behavior. Obviously, it's fine for sequential consistency. For Java memory model, it's arguably okay. So there are some problems regarding out of thin air. However, it's not that obvious as it is in C++. Yeah, there is a comment in the chat that Java forbids out of thin air. Actually, it's not true. I can show you some examples, but let's skip it to the end of talk. And so what's about C++? In C++, the situation is bad. Yeah, so in C++ situation is bad. In a sense, that's the standard allows out of thin air. You will never observe it in real life with the current compilers and the current CPU architectures. However, the specification is broken, so it means you cannot reason about programs as you could if you would have the guarantee. And actually, this is what the community around weak memory models tried to solve for last, I don't know, like 20 or 25 years in different settings. And in terms of C++, it's definitely more than 10 years already. So let's now chat what's the cause of out of thin air in C++. As I showed you before, this program in C++ may end up with A being equal to B and being equal to 1 in the end of execution. But now let's start with a slightly modified example to discuss the C++ memory model. So here, the right thread is exactly the same as it used to be in out of thin air example, but in the right one, in the left thread, instead of having a control dependency, we just have a write to Y. And now let's see how the memory model defines behaviors of this program. So the C++ memory model is called declarative or axiomatic memory model. What it means that each allowed execution of the program in such memory models is described by some execution graphs. So here we have one example of such graph. And in these graphs, each vertex is some memory access. So here we have two types of the accesses. It's read accesses and write accesses. And the accesses are marked with the corresponding locations and values. So here, essentially, we have a read access to X, which gets the value 0. The same for Y. So this one corresponds to this read instruction. This one corresponds to that instruction. And we also have a write to Y, which corresponds to writing in the left thread. So the edges in these graphs, they present different relations between the memory accesses. So in this particular case, we have one edge, which is called program order, PO, which actually totally orders accesses of the same thread. So this is one execution of this program leading to result A being equal to 0, B being equal to 0. The other allowed execution of this program leads to result A being equal to 0, B being equal to 1. So here, since we get B being equal to 1, we execute the then branch and write 1 to X. So this is why we have one extra event in the graph. Also, there is one additional type of edges in this example. So here we have so-called read from edge, and it relates writes with the reads. So to each write in the graph, there should be read from edge from some write. However, as you may see, there are no edges to the reads reading the initial value. So this is the thing I decided to make examples a bit smaller. But actually, you may think that there is some initial writes. Oh, sorry. There are some initial writes to both locations, and you have read from edges going to, going to the reads Yeah, okay. And the last allowed execution of this program, this is where you get a being equal to 1, b being equal to 1. So here, as you may see, there is some cycle on the edges. And like most of the weak memory behaviors could be explained by some cycle. But this one, yeah, this one is allowed, and it's fine in the sense that it's could be reproduced on ARM machine. So as we see in the name of this type of memory models, there is word axiomatic, and actually it is because usually there is a number of axioms which filter the events. So, for example, in C++ memory model, there's an axiom stating that PO united with some subset of read from edges should be acyclic. However, in this particular example, if we assume that all accesses in terms of C++ are like normal accesses or relaxed accesses, then you don't get these RF preserved edges or synchronization edges. As if you know a bit more about the memory models, you may know that that should be synchronization edges. So now let's take a look at this execution a bit more. So we now have two programs, this one and that one. For both of them, we could construct these execution graphs because the machinery which constructs the execution graphs allows us to do that. And now we should either allow this execution graph or disallow in C++ memory model. So the reason to allow it is because ARM memory model allows it. However, we don't want to allow it. So we kind of want to allow it for this one, but not for that one. But currently, it's not possible. We cannot distinguish. These are exactly the same graph. So if we have the same set of axioms, then we would either disallow this outcome for both programs or allow for both programs. So what we could do. So actually, if we take a closer look, you may say that there is a difference between these programs, which is kind of obvious, and maybe we could reuse it. So here we have obvious control dependency. As here. And we have a control dependency here, but nothing like that here. So maybe we could use it somehow. And actually, yeah, this is a solution for hardware memory models. So hardware memory models, they track the dependencies like that, and they disallow cycles of the form read from and dependency. However, let's take a look at the third version of our program. So here, instead of having a simple if with then branch, we have if statement with then and else branches being identical. So the problem is that we would like to be able to optimize this program to that one. This is a common compiler optimization to remove a conditional if there is no need for that, right? And however, if we construct the graph with the dependencies as we discussed before, this would lead us to the both threads having control dependency. And that means we won't be able to do the optimization if we want to disallow the graphs of such shape. So actually, because a compiler could remove the dependencies like that by changing the code. This is not what is used in programming language memory models. But maybe there is something which still distinguishes these three programs. And yeah, there is something. And this is something is that actually the control dependency we just added, it's so-called fake control dependency. So it's not like real control dependency. And the solution to the problem to forbid out of thin air is actually to count only real dependencies, not fake ones. But it's a hard problem. And there is no really good definition what is fake dependency, what is not. For some examples, like this one, it's extremely clear how to say if it's fake dependency or not. For others, it's more complicated. So like coming up with machinery which calculates and distinguishes, calculates dependencies and distinguishes fake dependencies from the real ones. This is actually what was driving the research around solving out of thin air problem for a number of years. So we already know the problem with out of thin air. So now let's discuss some solutions. And one of the straightforward solutions is a modification of C++ memory model done by Ori Lahav and his colleagues in 2017. So they proposed to add extra condition to C++ memory model and to forbid all PRF cycles. So essentially, it would disallow load buffering behaviors in the C++ memory model, and thus will disallow out of thin air. So now let's discuss a bit what should be done to compilation process to forbid PRF cycles. And actually, it's just enough to forbid reordering of reads with following program order following writes. It means that we'll need to enforce edges, program order edges between reads and writes. So let's take a look at some cycle with PRF. We know that program order is transitive, so we could slightly simplify the cycles. Also, what we did to simplify the thing is that we know that some read from edges, they also program order edges. Some read froms are external ones, so they go from one thread to another. And it means that we could simplify the picture to be, due to transitivity of program order, to be just a number of PO edges followed by RF minus PO edges. So now we know that all read from edges, they start with a write and end with a read. These external reads, this is something which is respected in all hardware, in a sense that in a cycles, which if other parts are not allowed by hardware to reorder, it means that the whole cycle is forbidden in a memory by a memory model. So it's enough to forbid reordering on these edges. So how to do that? So we need to do two things. First, we need to restrict compiler optimizations from reordering reads with following writes. And also we may need to do is to put a fence between reads and writes. And actually, this solution is cheaper for C++ than to Java, meaning that if you do it, then you may do it in C++ more precisely, more fine-grained, and slow down your programs not that much as you would have to do in Java. So why is that? And actually, this is because C++ has undefined behavior. So what is undefined behavior? Suppose we have one more program. So here we have some message passing pattern. So we want to pass some information through location data. So in the left thread, we write to the location, then we assign the flag saying that the data is ready to be transferred. And in the right thread, we wait for the flag to be set, and then the read from data. So if we write the program like this in C++ with data and f being like normal int variables, then it would lead to undefined behavior. And the reason for that is because there is a data race between accesses on normal locations. So actually, these access and these access are in data race. So for Java, because it doesn't have undefined behavior, this program is fine. So it will have some defined semantics, although it may print 0 here. And the reason for that, because these two accesses might be reordered. And actually, it could be done both in Java and in C++. But what the undefined behavior gives us? So if we say that our f location is not a normal int, but so-called atomic int, and if we mark write accesses to the f location as release access and the read access to the location as an acquire access, then it would essentially give us synchronization between these two accesses. Here I wrote synchronize with edge. And this would mean that the only outcome possible here would be to print 42. And there will be no data race which leads to undefined behavior in C++. So in Java memory model, there is also a special tag which we already discussed, volatile, for similar situations. And the difference with C++, as we discussed, is that you in Java memory model you get some weak guarantees. So in a sense that like many outcomes are allowed. In C++, any outcome is allowed if you have a data race on a normal memory cell. So the counterpart of normal accesses in Java is relaxed accesses to atomic int. So they also have weak guarantees if there is a data race on relaxed accesses. However, it does not lead to undefined behavior, unlike accesses to a normal ints. So what does it mean? What it means that the subject to out of thin air in Java memory model is all accesses, whereas the subject for out of thin air in C++ is just some relaxed accesses which are explicitly marked as ones being used for synchronization by the type. So it means that in C++ memory model, it's enough to forbid reordering of reads and writes, which are atomic ones, to forbid PORF cycles. Whereas in Java, you would have to do it for all accesses. So this is why the solution RC provided by RC11 memory model is more efficient for C++ setting. Yeah, so if we introduce an extra criteria of no undefined behavior, then C semantics and Java memory model, they have no undefined behavior, so they have like a nice property there. whereas C++ and RC11 memory models, they have undefined behavior, so it's not good in this criteria. So as I already said, to forbid PORF cycles in C++, it's enough to just respect program order between reads and writes. On atomics, so how expensive is that? There is a paper doing so in LLVM setting. So what they did, they restricted compiler optimizations to forbid reordering between reads and writes and put a fence between reads and writes. However, it happens so that in LLVM there are no compiler optimizations which reorder such accesses. So actually, you don't need to do anything. And in terms of fences, in x86, there are no load buffering behaviors, so you don't need to do anything. On ARM, you would have to do something, and there are different strategies to disallow reordering of reads and writes. So the most straightforward one is to insert a memory fence, but actually the research showed that it's more efficient to just insert bogus conditional branch between such reads and writes. And interestingly enough, slow down on big programs used for testing this approach showed that on ARMv8, the average slowdown is 0% with maximum slowdown 6.3%. So it essentially means that for many applications, for many languages, it would be okay to go this route. Although, for example, C++ community still may argue that we need to be able to get the maximum performance from the hardware, so it might not be applicable for C++, but for other languages like Java, for example, it could have been a nice way if there was the same. So for Java, it's also not good because of the absence of undefined behavior, but it could be the way to go for safe languages. So as I already said, preserving this program order between reads and writes is good if you do it only for atomics. So what's about case of Java? So for Java, similar testing show that it would be a bit more expensive, and it would lead to 3.1% slowdown on average and 17% slowdown at max. So it's still quite modest and means that the solution could be applicable even for languages like Java. Okay. There are some other theoretical models to solve the problems, and like the promising memory model, the weakest memory model, and MRD model with different advantages and drawbacks. Unfortunately, we don't have much time to talk about them today. Probably we'll discuss them in some other talk at the seminar. But the problems with these models is that they actually, if we introduce one more criteria, simplicity of the model, then we would realize that these models are quite bad in the sense that they are quite complicated and very different to the memory models which are already there. So essentially, that's it, what I wanted to talk about today. To wrap up a bit, I would like to state that the existing memory models of languages have major issues. However, there are some solutions which, based on different compromises, how much performance can you sacrifice for nicer semantics, how complicated your memory model could be, can you have undefined behavior, and things like that. Yeah, so that's it. Thank you. If you have any questions, I would be happy to answer them.
The only thing I think you promised to address and didn't was about out of thin air, which is forbidden by Java or not forbidden.
Yeah. So yeah, the problem there is that there is no clear definition out of thin air. Yeah, actually, I think I won't be able to show the example right now. So I'll probably postpone this question to a later email if it's interesting. But yeah, so the main problem is that first of all, the memory model of Java, there is no clear definition of out of thin air. So and there are some examples showing that Java memory model not completely disallow what some people expect to be out of thin air. So yeah, it's like a long talk. Sorry that I won't be able to cover it now. Yeah, so there is a follow-up question is about out of thin air in Java. No, actually, like most of the people say that there is no out of thin air in Java memory model because this is what it claims. But yeah, there are problems related to both compilation and the DRF guarantees. And yeah, yeah, probably I'll add more details in the later revision of this talk. Thank you for the questions. Yeah, okay. If there are no other questions, thank you all for listening and coming.